Now that we saw the formulation of the margins maximization with SVM, we will look at how this translates into an optimization problem. So at first, we need to go back into some basic elements from that you probably saw in your calculus or college courses on maths. Is for solving optimization problem under constraints. So the point here is that we want to maximize some value. So we have some function f, for which we want to find the x that is maximizing f. So basically, when we are just dealing with this, a simple approach that you know is to compute the derivatives of f according to x, make this equal to 0, and figure out the value of x with this derivative equal to 0. We made use of that before in the course. But now we will add a constraint. So we'll say, yeah, we want to maximize f of x, but we want that the solutions we find here have an x that allow to respect the constraint that g of x is equal to 0. So this is our constraint that we want to respect. And this can be solved with the use of a Lagrange multiplier. So how we can do this is to define a new function that is basically the gradient of f plus lambda, and lambda is different from 0, gradient of j, and all of this equal to 0. So by solving this, we are able to figure out the value of x that is both maximizing f, but respecting the constraint over g. And so there is that parameter lambda. And if we develop this a little more, we've got what we call the equation with the Lagrange multiplier. So this lambda is basically the Lagrange multiplier. So we see we have a new criterion, which is called big L, which include the x, but also the lambda. And that criterion aim at, it is including f plus lambda g. And as such, we are able to obtain the maximum like we are used to do. We just compute the gradients on L, so the partial derivative according to all x values in the vector x and the lambda value, and make this equal to 0. And then we can analytically get into some solutions as far as f is following what we assume as correct for using that method for solving it. The point is that if we are in fact interested by the x, in the end, we don't care much about the lambda value. The lambda value is in fact something, an element, a multiplier value added here in order to solve our problem. But in the end, we care often just on the x value. We don't care about the lambda value, so we could just eliminate it from the equations directly by manipulating it. So an example on the use of the Lagrange multiplier is to say, okay, we are looking to maximize a given f function, which is basically 1 minus x1 square minus x2 square. So this is the function we want to maximize, but we want to constrain the solution to be following the constraint that x1 plus x2 minus 1 is equal to 0. So if we formulate this optimization problem with the Lagrange multiplier, we have this big L function, which is basically f here. So this is the same thing than there, plus lambda times g here. And from that, we are solving it by getting the gradient of L equal to 0. So we have 3 partial derivatives. The one according to x1, which tells us that minus 2 x1 plus lambda is equal to 0. Similarly, for x2, it's minus 2 x2 plus lambda is equal to 0. But we are also computing the partial derivative according to lambda. And now we have x1 plus x2 minus 1 is equal to 0. And if you are looking at it carefully, you can see that the last one, in fact, is the function g. In fact, it is exactly what we are looking for constraining g to be equal to 0 to follow that constraint. So this is nice because we are kind of embedding the constraint in the equations to solve. So by developing this system of equations, we are able to figure out that when we have three equations, three unknowns, we are able to figure out that x1 should be equal to 0.5, x2 should be equal to 0.5, and lambda should be equal to 1. This is where we will maximize f while keep respecting the constraint. And visually, the same problem looks like this. So basically, our constraint G, which states that we want this to be equal to 0, is constraining us to be on that dashed line. So that dashed line is the line with the only points that are allowed, only points that are respecting the constraint G. And we see as the colored circles, the different contour plots, the different contour lines corresponding to the function f. And in fact, without any constraints, the value that is maximizing f is really the origin 0, 0. This is where these things are disabled, and we have an f value of 1. As we move away from the origin, we get a lower and lower f value. And so I would say values, lines corresponding to equivalent values on f are these contour lines here. So we see that maybe overall that first circle, it's one value. Over, I would say the third one is another value. Over the last one, it's again another value. But as we go into bigger circles, the value of f is lower. And so we can see visually that the point where we will keep being on G, but minimize the value of f is in fact that point here. This is really the position where we will get the maximum f while being on G. And this value, I would say, is corresponding, in fact, to the minimum distance over J to the origin, because this is what we are looking for. So the Lagrange multiplier allows us to solve that problem quite elegantly. Now we are looking at Lagrange multipliers with inequalities. So we were considering that G is equal to 0. Now, if we look at G that is, for example, higher or equal to 0, how can we manage this? So in fact, in that setting, we have two possibilities. First possibility, we are facing an inactive constraint. It means that the absolute maximum for f is in a position where G is always respected. The constraint is always fulfilled. So we don't care much. It implies that the lambda, which is integrating the G equation, is equal to 0. So this is like the case where G is disabled. It is not useful here. We are able to find the maximum f within that the domain given by G. The second possibility is the opposite. This is where, you know, the optimum value on f is in a position that where the constraint given by G is not respected. So this is a place where we will, in fact, find the maximum f for which G is equal to 0. Because this is at this point of G equal to 0 where we will maximize f usually. In that case, we know that the gradient of f will be equivalent to minus lambda gradient of G. Why? Because you know with the formulation over L, we have something like gradient of f of x plus lambda gradient of J of x is equal to 0. This is where we have our partial derivative, and we want to solve this. Okay. And so these conditions correspond to the so-called Karush-Tucker conditions. We know that G of x is greater or equal to 0, lambda is greater or equal to 0. And we know that at least one of these two are equals to 0 at the optimum. So it's either lambda, it's at lambda times G of x give us 0 because one of these two are equal to 0. And when we are looking to minimize f of x, because we give some explanation on maximization, but in fact, in learning, we are generally minimizing the loss function. So we want to minimize f of x subject to a constraint on G g greater or equal to 0, we are subtracting the constraint here. So we are formulating this slightly differently. We are using the minus sign. So f of x minus lambda g of x with lambda greater or equal to 0. This is what we want to solve. And solving this is basically true. Computing the partial derivative and so on. So closing the parenthesis here on Lagrange multiplier, we are getting back to the SVM optimization problem. And in fact, the SVM optimization problem, if you remember well, it is to maximize the margin. So the margin, if you remember well, is rho is equal to 1 over the norm of W. This is what we are looking for. But with SVM, in fact, we are looking to maximize 1/2 or times W norm squared. So it goes in the same direction, but we are using this square factor because it kind of helps in terms of developing the equation, and it also allows us to make a better optimization in some ways. It's relatively an advanced topic, but the point is that we want to minimize 1/2 times the norm of W square, and this is subject to these constraints. We say that for each sample, we want each sample to be well classified, and even more, we want them to be well classified, but outside the margin. And so we want the product of, for each xt, W transpose xt plus W0, which is h of xt basically times RT. We want all this to be higher or equal than 1. And this for all the samples of our data set. So we don't have one constraint, we have n constraints, 1 per sample. So dealing with this maximization function, with one maximization function to get, but with n different constraints, we are able to develop the equations. And this is in fact a typical form of what we call quadratic programming problem. So in optimization, operation research, this is super well known. This is a regular form for optimizing. It is quadratic, in fact, because of this, but this is correct. And the good thing with that is that there are many solvers, many methods that have been proposed to find the exact solution for this problem. It's not just anymore to, when we do gradient descent, for example, we tend to get into good solutions, but it depends on the starting point. It depends on many things. We may be stuck in local minima. Here with quadratic programming, we have guarantees that we will reach an exact solution and always reach the same solution with the exact same setting. It's kind of an exact method for solving the problem. So now if we go back with our Lagrange multipliers, we will convert this minimization problem with 1f and n different constraints to that thing here. So basically we state the L function as function f here, which is what we want to minimize, minus minus lambda g. But here we have more than one constraint. We have n different constraints. So we are summing for each constraint. And we have the alpha t here, which is corresponding to our lambda when we presented the Lagrange multiplier, but we changed the name because usually we say alpha here for SVM. So we have the alpha t here, which is the Lagrange multiplier for respecting a constraint over one sample of the training set, one of these guys here. And then we have the constraint here. So basically it states that we want RT time h of xt minus 1. So all these things, but moving the +1 on the other side. So we say -1 here, and we want this to be greater or equal than 0. So this is why we are adding -1 here. And so this corresponds to our new formulation with the f function to minimize plus the constraints. And if we just kind of move the things around, we are able to get that thing. We are able to have a summation of alpha t RT W transpose xt plus W0, and also, because this is coming from that thing, so minus alpha t times minus 1, we are able to adding plus the sum of alpha t over all over the n alpha t's. You may have observed that we have the subscript p here, which correspond to, in fact, to state that this L function is the primal formulation of the problem. Because in optimization, it's quite common to say that we can convert some problems from their primal form to their dual form. It is kind of an equivalent form, but where we substitute many variables, we change the problem, and we are even changing often the optimization direction. We are maximizing one while minimizing the other. And here, if you look at these things, we have different variables. In fact, we want to solve LP by first optimizing, minimizing the function over W0. So, we have this W here, W0 in that equation, and we want to find the right W0 to use. And we also want to maximize by being sure that alpha t is greater or equal to 0. We are not allowed to get negatives alphas, like we are not able to get negatives lambda, because when we are in a negative value, it's kind of not respecting the problem of according to the constraints we put in there. And the point is that we want to minimize according to W0, and we want to maximize according to the alphas. So it's kind of, saddle point solution, a saddle of a horse. So we can see that we have things like this here. So on one direction, it's kind of going in that way where we try to minimize it. But on the other direction, it's kind of maximize. So we try to find the minimum here, for example, over this function, but we also try to maximize according to the other functions. And this is difficult to manage. This is not something that is easy in terms of optimization to reach. We can get some instability because maybe going in one way where we try to minimize will break things in terms of minimizing. So we will simplify this primal formulation of the problem by defining a dual formulation. And this is achieved basically by eliminating the W using the partial derivatives according. So we will get W0 eliminated by computing the partial derivative of the primal formulation here. And we will get this derived according to W's equal to 0. Same thing for W0. So if we want to pass on the dual formulation, we have our LP here. We are still working with that formulation with W's and alphas. And as such, we are computing the derivative here. So the derivative according to W. So here we are making some tricks. We are directly dealing with the vectors in terms of the derivatives. That's okay. That's, I would say, brain gymnastic to do, but that's okay. And that will simplify a lot the developments here. But, in terms of making the complete developments, it's often good to pass through individual variables to kind of get it right at first, but then you can simplify the presentation and the thing into derivative with vectorial vectors. So the derivative according to W here, given that we have something at power of 2, it goes back to some kind of W here. And that part here, we have that W here. It's kind of eliminating that because derivative of x is equal to 1. So we have that thing here that corresponds to that thing here. And the rest is equal to 0. There are no W's here. So with this formulation, we see that W minus the summation of alpha t RT xt, all this is equal to 0. Well, I'll just move the summation on the right side. So we have W is equal to the summation for all samples of the training set of alpha t RT xt. Now, if we do the same thing, but with W0, We just care about that W0, and basically this is derived as 1. And so we just keep that element. So the summation over T of alpha T or T, all this being equal to 0. So with this thing here, we can reformulate stuff in that way. We will first expand, this notion of norm of W square is completely equivalent to W transpose W. So if we just take the vector W, multiply by itself, but W transpose and W, we get into a scalar that corresponds to the square norm of W. And then we are also developing this thing here by isolating the W that is there and isolating the W0 that is there also. So this is just a way to reshape the primal version of the problem. And then with this, we can get into something as simple as that thing. So how can we achieve this? So basically, okay, this development is kind of not that obvious, but you can make it on the side in your own place as an exercise. But just one thing to look at is that, we move from a plus to a minus, because in fact, all these things, here and there can be simplified. First, we know that this thing is equal to 0. So all this thing is canceled. We know here that we have W transpose, but we know that that thing is equal to W. So it looks like that we have something such as 1/2 W transpose W minus W transpose W, which is equal to basically minus 1/2 W transpose W, which is that here. So we have that here, we have that is kept as is, and we have this thing that is set to 0. This is how we achieve this. And if we go further along, we can substitute in this thing WTW that result, which allow us to eliminate completely the W. We've got that thing here. So the summation over T and S are both from T equal to 1 to N and S equal to 1 from 1 to N. But we use a different index to avoid confusion, because it's dealing with the same variables over the same range of indexes, but these are not used with the same index, is not necessarily used simultaneously. We have the index over T and over S to differentiate the which alpha is used with which other alpha, and which R is used with which other R, and so on. So this is the new formulation here we have. And the nice thing is that we don't have any more W and W0s, we only have alphas. So all the alphas are enough to define our optimization problem. So going back to the formulation we had before, now if we go into the dual formulation with the Lagrange multipliers, by eliminating the W0s, we are able to get that thing. We want to maximize minus 1 over 2, summation over T, summation over S, from S equal to 1 to N, T equal 1 to N. And now we have the alpha T, alpha S, RT, RS, XT transpose XS, plus summation of the alpha T. And this maximization problem is subject to the fact that alpha TRT is equal to, sum of them is equal to 0, and all alphas are greater or equal to 0. So this new problem formulation, which is exactly equivalent to what we have before, but it is simplified in terms of the parameters, because we don't have to deal with W's anymore. This formulation depends now on the size of the data set instead of the dimensionality. So we are dealing a problem according to its size, its training set size somehow. That's good in some ways, in many ways, in fact, because the dimensionality can be relatively big, depending on the context on where we are working, and depending also if we are dealing with approaches that are including a kernel, which we will see later on this week. So this form with the dual formulation using the Lagrange multiplier is resolvable by quadratic programming in the sense that we just use this, we can plug this into some solver, and the solver will give us a global optimum. So if there is a feasible function, it will be found in polynomial time, and we will get really the global optimum to a given problem. The complexity in time with naive algorithms is something like O power 3, O n power 3. So this is a big O notation. So it means that in time, it goes with a power of 3 over the size of our training set. So big training sets can be really, really long to optimize, but usually with hundreds and thousands, that's fine. That's kind of well manageable. It's more with hundreds of thousands or millions of samples where this will be really problematic. And in space, we need, I would say, something big O in big O notation, n square space memory basically required to store all this to get everything stored and processed. And this formulation allow to use kernel functions, as I said, which will be presented later on this week. So with our new formulation, we have one alpha t per training data. So each data has an alpha that is associated to it. And the point is that the majority of alphas are equal to 0. So the majority of constraints are disabled because when a data is correctly classified with an age that is bigger than one or less than 1, not equal but bigger than 1, and not equal but less than -1, and correctly classified, it is not in the margin, it is not on the frontier, its alpha is 0, and that's fine. It is kind of disabled or not used directly to position the hyperplane. But for those where the alpha is different from 0, it is positive because negative alpha is not possible. So if we have an alpha greater than 0, we are dealing with what we call a super vector. So this is why we call this super vector machines. We define the data with a non-zero alpha as super vectors. And as such, this is interesting. We can even also, we need somehow to define the set of support vectors here. So we have this thing here where we say, okay, the set of all alphas for which the alpha is greater than 0. And we use that thing, for example, to compute the constant W0. Some people who are good to observe may say, well, is it really required? Because only with one sample, we should be able to get the W0 value. Right, but it might be unstable. So we care about all data that are on the margin. So all data with non-zero alphas, and using this and computing the expectation, so of the RT minus W transpose XT, which correspond to our W0, but not just for one sample, but for all samples that are support vectors, we get a better estimation, a more stable in terms of numerical computation of W0. And this expectation is basically empirically evaluated to say, okay, over all samples, over all alphas that are non-zeros, let's compute RT minus, and this thing here is basically equivalent to that, but getting rid of the W. So just replacing the W with what we found before in terms of defining W's as from alphas and XTs. And now if we have the W's that are obtained by quadratic programming, we have the W0 that is obtained in that way. This is one way. How can we do the classification of samples after that of test cases, given that we haven't explicitly computed W and we still are able to not use it? I mean, we don't need to get W's evaluated here. the post-training data evaluation, when we have a trained model, goes that way. It's basically, it's equivalent to summation W transpose X plus W0. It's kind of equivalent, but we replace this with the right equation. We replace this with summation over alpha T RT times XT transpose. So sorry, not the right thing here. In fact, this thing corresponds to our W. So summation over all training samples, alpha T RT XT transpose times our X value. This is the one we want to classify, plus W0, which is obtained that way. So this is how we can evaluate the age value of X after the training only from the alphas and W0. So to illustrate this, we have some examples with, on the left, we have a suboptimal margin. So this suboptimal margin is a solution that is achieving 100% accuracy. But what we can see is that we have some margin. Yeah, we have a margin, and this margin, it seems to be good. This seems to be quite reasonable, but it is not maximized. In fact, the solution that is maximizing the margin is the one on the right. So this one on the right is maximized. We really try to push away the maximum distance from the upper planes, the margin. We want to get the biggest margin possible. And if you can see this in 2Ds, it's kind of visually interpretable as having like two support vectors for one class and one from the other class in 2Ds. This is a solution in 2D. And these three support vectors are enough to define the separating hyperplane here, which is maximizing the margin to these samples. And you can see that the slope of the hyperplane here corresponds to the slope of the line connecting this support vector with that support vector.